Hey, this is Horner. We're going to look at a couple sections. The first section is on transformers, and the pictures below here just show a couple of different, really very simple transformers. Transformers do exactly what it sounds like, is they take a certain amount of electric potential, or EMF, and they convert that from either going from a higher EMF to a lower EMF or from a lower to a higher. Typically, if they go from a higher to a lower, we call that a step down. So you'll notice that there's two types of coils here. This one's a little harder to see than this one is. But essentially what they do is they take a wire and they wrap it several times. And you'll notice that we call those the N number of coils around one side of a soft iron core. And on the other side, we have another wire. And what happens is the magnetic field is generated throughout this coil, and we can take voltage. Maybe we say that this one's like 10 volts, and we're going to step it down to 5 volts. So when you plug in something like your iPhone charger or any type of charger like that, you don't want 120 volts going into your phone. That would fry it. So instead, there's a transformer in that big box, and that box that you plug into the wall will take that 120 volts and reduce it all the way down to somewhere around 12 volts or 5 volts, depending on what it is. Typically, I think it's 5 volts for those. But that's essentially what a transformer is. So if you have an alternating voltage and it is applied to that primary coil, that secondary coil then makes it basically just step down is what we call it. So this is an example of if I have EMF E1 and it's induced in the primary coil. Here's the number of turns. Here's that change in flux over the change in time. And if we ignore the resistance and the coil and all kinds of other energy losses that really happen, that EMF is equal to the AC voltage. So that'd be 120 volts on that E1 side. On the E2 side, this has got a different number of turns, so we have the same equation. And in the instant that flux through each turn is, of the secondary is equal to the flux through the turn of the primary, so we can set these two equations equal to each other, and we can get rid of, you'll notice that we can get rid of the change in flux over the change in time since those are equal. Once we do that, we say that the EMF number 2 over EMF number 1 is equal to the number of turns in the secondary coil over the number of turns in the primary coil. And from that, we can actually determine all kinds of great things. Basically, we can use this turn ratio to go ahead and figure out what that new EMF would be based on the number of turns. So I've talked a lot about a step up or a step down transformer, depending on whether I want that secondary EMF to get bigger or smaller. And I can actually use the same transformer as either a step up or a step down, depending on which coil is used as that primary. So I can flip it essentially. In an ideal transformer, the power losses in transformer are negligible, so we don't have to worry about those. Most transformers are pretty efficient, so we can ignore power loss. And the rate at which energy is supplied to the primary is equal as it is to the secondary. And since the powers are the same, we can look at how the current then is the inverse ratio of the EMFs. So notice here I've got current 2 over current 1 is equal to EMF 1 over EMF 2. So notice that here's the 2's, here's the 1's. They are an inverse of the ratio of the EMFs. So let's go ahead and let's use this example to kind of help us understand transformers. So here I've got a transformer inside of a charger for a cell phone. We talked about that. It has 500 primary turns in the primary coil. It supplies an EMF of about 6.8 volts when it's plugged in. And that household EMF here has an amplitude of 170 volts. So they first want to know how many turns does the secondary coil have, and then they want to know if the current drawn by the cell phone is 1.5. They want to know what is the current in the primary. So I'm going to skip over the strategy and go right to the solution. Here's our equation for the step-down transformer. We know that we start with 6.8 volts. I'm sorry, we want 6.8 volts. We started with 170 volts, and we multiply it times that 500. So that tells us that the number of turns on the other side, so where your cell phone is 20. And then from that, we can also figure out what is the current then that's supplied to your cell phone. 1.5 amps would probably be too much, so you'll notice that we've taken that secondary EMF, which is 6.8, divided it by the primary EMF, which is 170, and we multiply it times that 1.5 amps of current going through, and we end up with 0.06 amps. All right, so that is 20.6. We're not going to look at 20.7. It's on eddy currents, and I'll just show you a quick demonstration of eddy currents and why they're important. For 20.8, these are about induced electric fields. So if I have a conductor moving through a magnetic field, we do get that motional EMF because of the magnetic force on the mobile charges inside of that conductor. So since those charges move along with the conductor, they have a non-zero average velocity, and the magnetic force on them pushes them in a complete circuit. So we've already done that before. If they want to know what causes an induced EMF in a stationary conductor in a changing magnetic field. So now the conductor is at rest, and the mobile charges have an average velocity of 0. The average force on them is 0, so it can't be that the magnetic force that is the thing that pushes the charges around the circuit. So in an induced magnetic or an induced electric field, not magnetic but electric field, is created basically by changing the magnetic field that acts on the mobile charge in the conductor, and it pushes around the circuit. So we can use the same force law, which is F is equal to QE, and that applies to induced electric fields as any other electric field. So if I have an induced EMF around a loop, that's the work done per unit charge on a charged particle. It moves it around. So therefore, your induced electric field does non-zero work on a charge that moved around a closed path as long as it starts and ends at the same point. So in other words, your induced electric field is what we call non-conservative. So that's really important. The work done by an induced electric field cannot be described as charge times potential difference. So we've got to look at it a little bit different than what we have in the past. So here's for conservative electric fields. The source is charges. The field lines start on positive and end on negative charges, and it can be described by electric potential, and the work done over a closed path is always 0. But on a non-conservative electric field, this is one that is induced by a magnetic field. The field lines are closed loops. We cannot describe this by an electric potential, and we can see that the work can be non-zero because it is non-conservative. So that's pretty important. So looking at these electromagnetic fields, we can use Faraday's law to help us kind of go through this. And as we see in chapter 26, there's some things that we can do that deal with Einstein's theory of special relativity to kind of help us to see that. In one field, the induced EMF is due to the motion of the conductor, and another, the induced EMF is due to the changing magnetic field. So these are some things that we're going to kind of tackle just a little bit when we look at induced fields. Electric and magnetic fields are not really separate. They are very intimately connected. So this is one of the primary things that we look at in physics. So though it's advantageous in many circumstances to think of them as kind of differently, so you have an electric field on one side, a magnetic field on the other, the better view or the more accurate view of this is to think about something called an electromagnetic field. So typically what will happen, and we'll see this when we do electromagnetism, is you might have an electric field going one way, and then you'll have a magnetic field kind of crossing it, kind of like this. So it's kind of an interesting thing how these are 90 degrees separation from each other, and kind of how that works. So just really kind of an interesting thing that we'll be looking at later. For a loose analogy, a vector might have different x and y components in different coordinate systems, but they represent the same quantity. So an electromagnetic field has electric and magnetic parts, kind of like I was just showing you with those two sine waves that are offset by 90 degrees. And so we can actually see how those two things work together. There is a little bit of missing symmetry, so if I have a changing B field, it's accompanied by an induced E field. We want to know if that's the other way around, so does changing an electric field make an induced magnetic field? And the answer to this, which is central to our understanding of light and the electromagnetic wave, is basically yes. So we will look at that in chapter 22. I think earlier we were talking about chapter 26, which is relativity. We won't look at it. But that's basically that. That's what we need to know for these two sections out of your book.